All attendees are in listen-only mode.
Hi, welcome to today's ADAPT webinar. We appreciate everyone attending, and today we're going to discuss evaluating modeling, analysis, and design for a two-way reinforced concrete slab without any post-tensioning. And we wanted to introduce this webinar. Really, a lot of times clients think of ADAPT as just a post-tensioning company, but we do offer solutions for both regular reinforced concrete and post-tensioning. We wanted to show you this webinar just really to introduce you to the ease of modeling and extracting results for a two-way slab in ADAPT Builder. My name is Spencer Lee, and I'll be conducting today's webinar. A couple of housekeeping notes. One, if you have any questions related to the webinar, feel free to ask those by just raising your hand and typing the question in. There should be a panel on the GoToWebinar floating panel on your screen, and I'll try to answer those as we receive them. If you do have questions about any other topics related to ADAPT, whether it be licensing or another program or troubleshooting some model that you might have that might be unrelated to today's webinar, please feel free to contact me after the webinar, and we can address that outside of this forum. So, and you can also send questions to support@adaptsoft.com. So we'll go ahead and get started today. We are going to be recording today's session, and we will send that out to you here in the next couple of days, the recording for today's meeting. So on the screen you should be seeing my model here, and we're going to look at a single level model in ADAPT Floor Pro. This is the module of ADAPT Builder that we are currently using. And let me just navigate to a top view. This just has 3 bays in the X direction, 4 bays in the Y direction. We're working in metric today. The first thing we're going to cover really is how do we model a slab in Builder. What are the ways that we can model a slab, either by modeling from scratch or importing from a CAD file or a Revit model, let's say. And one thing to note is that today I'm using build 2 of version 2016. This build will be released on Monday of next week. So you may see some things in this build that may not be familiar to you, and specifically in the modeling interface, and I'll try to describe some of those features as we're moving along in the webinar. So we'll come back to this model as our working model here in just a moment, but we first want to kind of explore the different ways that models can be constructed. And we're not going to spend too much time constructing a model from scratch, and we'll essentially use the wizard, but we wanted to make note of the settings that will be selected in the splash screen when you launch Builder. In this case, we're using Floor Pro, and we're not really tapping into the multi-story analysis capabilities of the program. We're just saying we want to just evaluate a single slab, determine what the reinforcement is, make sure the deflections are set up, and we have the opportunity to evaluate deflections, both cracked and uncracked deflections, which we will also set up. And Floor Pro is the module that gives you the ability to both analyze and also design an elevated slab. And if we look down at the bottom, we have basically a few selections here that can be chosen. We have the system of units. Obviously we have American SI, MKS units, and also the design scope. This is the more important of the selections if you're comparing it to being able to model with post-tensioning or without post-tensioning. So if you open the program in RC only design scope, this means that the capability of modeling PT is suppressed. You do not have that ability to model PT when it's opened within this design scope. This design scope also turns on and it enables the program's ability to calculate middle strips automatically for the user if the user wishes for the program to do that. So we'll talk about that when we're looking at strip generation. And then we also have some import and export options. We have the Revit import, ETABS import, and STAD. This ETABS and STAD both stem from our integration console, where you can import a model from ETABS and generate an adapt model from an ETABS model. And currently that particular integration console is in beta. It will be commercially available here within the next week or two, the ETABS integration console. So we'll just say okay to this. The first example we're going to show in terms of modeling is how can we just model using the internal wizard for Builder. And this obviously is somewhat restrictive and constrained. You have to model specific bays, numbers, spacings, and it allows you to model something that's fairly simple, but it is available. So if we go to Build, we're going to select the floor wizard. In the floor wizard, we're going to just assume we have, let's say, in the X direction, 3 spans, similar to our base model that I showed a moment ago. And we'll say the length of the spans is 27.5 feet. The column size in the X direction we'll say is 18 inches. And the number of spans in the Y direction is 4 spans. We'll say those spans are 25 feet. Column size we'll say is 32 inches. If it's a multi-story model, you can also replicate the floors, just inputting the stories here. The slab thickness we'll say is 10 inches for this slab. We'll go through, we can set up loading, just basic gravity load. This is uniform superimposed dead load and live load. We'll leave those values as they are. And then the top and bottom story heights. We're currently building the model at the current plane, which is the first elevated plane in the series of levels that the program will default to. We'll say end, and the program builds us this very simple model. It looks like there's nothing there, but if we rotate the view, we have the loading, we have the live load that was created, the uniform dead load that was created. The program assumes only supports at the current plane and below, so we only have columns below the slab. So if I wanted to copy those up, I could just Windows select these columns, for example. I could use the option either from the Story Manager toolbar to copy and move vertically, or I can do this also from Modify, Copy, and Move vertically. So here we'll just copy those up one time, and those columns get copied to the level above. So one other thing to note, when we generate a model with the wizard, the program will also just generate the design strips for us. So if I turn on the X and the Y design strips from the graphical control panel, this is also, technically it's called the Select Set View Items. Informally we call it the blue eyeglasses or the control panel, let's say. And we'll say OK. You can see the program has generated strips in the X and the Y, or I should say support lines in the X and the Y. So these support lines allow the program to first generate column strips and also to generate middle strips. And I'll use my marker here to kind of show what this is doing. So if we have this support line here, for example, the program is going to take the distance, let's say a quarter of the distance to the next support line and a quarter of the distance below the support line, and that will become our column strip. And this is kind of the boundary of that column strip. We have another column strip, let's say here, that the program will create. And then in between the column strip, we're left with an automatically generated support line and strip, which becomes the middle strip, which becomes, let's say, L/2, where L is the dimension between these two columns or support lines. We'll go ahead now and produce those strips. So if we go up to FEM, or excuse me, if we go to criteria, before we generate those and go to analysis and design options, you can see that when the program is opened in RC only mode, the program gives the user the option to have it create the column and middle strips. If we say yes, the program will generate them. If we say no, then the user is really left to create the support lines which would define the middle strips in this case. So we'll say yes, let's let the program do this, and we'll go to strips. I'll generate my tributary regions. You see that the program filled in the middle strips, and this is kind of a hard view to see what you're looking at. There's a lot of lines and colors in that, so we're going to use the blue eyeglasses to just filter what we're looking at. And I'll just turn on the support lines in the X direction. So now we're left with the support line and all of our design cuts for the middle and the column strips. And again, these middle strips are what the program has generated. So if we take this, and let's say we try to move this point, and we go back and we regenerate the strips, the program essentially overrides what we did, and it will generate a new set of strips for us. So if I just reset the view here, I'm just going to use a different tool to do this. You can see again it's actually reset that middle strip and extended it back out. Another way to view the strips, which makes it a little bit cleaner to look at, is if we use a toolbar which is called the Report Plans toolbar. And if I go to User Interface, under Report Plans toolbar, we'll use the option to display the design strips in the X direction, for example. Now we have our tributary regions that are shown hatched. So this is a nice clean view of what the breakout of the strips actually looks like. And we can also look at the same image but for the Y direction. Now if I go to the blue eyeglasses, I can also look at, for example, tributary regions. So this is another way to see just the region that was generated by the program. If I select a region and I want to manually modify the strip, if I take this strip, for example, and let's say I move it here, and then I take this and I stretch it down over here. So I'm making some manual modifications to the strips that the program created. Once I disassociate what the program has done with what I've done manually, I can now generate the strips again, but I can use the changes that I made as the new boundaries for the design strips. And I'll go back to strips, generate my design sections, but instead of regenerating, I'm going to actually use existing. And the program will now create the strip based on the existing boundary that I had adjusted. And again, if I go and isolate, you can see that for the column strip, it actually follows that boundary. For the middle strip, it follows the boundary, but the program still extends the middle strip to the projected extension of the column strip. So this doesn't give quite exactly what I need in this case. I wanted the middle strip to stop at this sloped edge, but because this column strip, which is used as the reference for generating the middle strip, because it extends out to the slab edge, the middle strip does also. So there's a little bit of give and take on how custom you can make your strips. In this case, we probably wouldn't make those adjustments to something so linear, but again, we're just showing kind of the tools that are available. Now in this case, if we just discard our strips altogether, and I say, well, I want to be able to just define my middle strips without the program doing it for me. So I'll go back to criteria, I'll select no to column middle strip, and now if I generate my strips, under the strip menu, we'll regenerate our strips. Now we can see that the sections are over the full tributary. There's no breakout of column/middle. It's just a full tributary strip. But we want the program to create those middle strips, but in this case we want it to create them based on our input for middle strips. So in this type of scenario, we would need to model our own middle strips. Remember, the program has created these, but I can always go in and generate new support lines, and I'll just go from end to end just as an example here. So there's one middle strip, there's two middle strips, And you'll notice that if we, right now I don't have my snap tools working for me, but if I pull down the snap toolbar here, turn on the snap perpendicular, we can just, snap perpendicular to these edges that I'm working with. And that becomes our set of middle strips. Again, I'll generate the tributaries, and we'll go back and just reset this. Now in this instance, it looks different than when the program created the middle strips for us, and hopefully you can see the difference here. There's about 10 times more design sections along the column strips than there are the middle strips. So each one of these lines is essentially a data point in the slab that we collect information for, moments, shears, and so on. And this is actually where the rebar is calculated. It's calculated for each one of these lines, demand or actions or integrated along the cut. And the program defines the number of design sections per span length. So in this case, this quote-unquote span length of this middle strip is from this point over to this point here. And so it fills that span in with the default number of cuts. So as a user, it's okay if you set the strip up this way for middle strips. However, you may want to generate more design sections. So if I just select all of these middle strips and select modify item properties, I'll tell the program I want more design cuts. I need more data points along those strips. So we'll go to support line, maximum number of design sections. In this case, I'll do 50 instead of 10 or 12, whatever the default is, and I'll regenerate my strips. And now we have more data points for these middle strips. Okay, so that is example one of how a model can be generated, and we went a little bit further with showing the automatic strips there, but we'll go now and look at example two. So example two might be if you have an AutoCAD file, like a drawing file. So I'll go ahead and create a new instance of using the program, and I'll import a CAD file, a DWG or DXF, from the location where the file is stored. I'll just select the drawing file. We'll just use something here. The program will ask me to do some calibrating of the file to scale it inside of our own user interface. So we'll go ahead and calibrate the file. I don't really need to move it into position, nor do I need to insert it at another plane other than what I'm inserting it at, which is the current plane. We'll say OK. And now I can calibrate. It's asking me at the bottom left, calibrate the drawing that you've imported, and I'll go from point A to point B. I know that this dimension is 20 feet, and I'll use zoom extents, and now I have my drawing file in the UI. And so now we'll use what is called the transform toolbar, and if I open up this toolbar, transform to structural components. You can also find these under Build, Transform. So we'll do this. We'll just select a slab. We'll transform that to a slab. I'll select multiple walls. I'll transform those to walls. I'll select a few openings here. There's several openings, but these are just polygons that we're just transforming over to these different components. We'll transform those. And then finally, I'll do the columns. So if I select these columns, and I can also do some window selection. You can also filter out layers. I'm not going to that extent for this slab, but there's a layer manager in the program, which is located right here, layer settings, and you can turn off and on layers in order to transform things more rapidly. So I transform my columns. I'm now left with a structural model that looks like this. And now I'm able to generate loads, support lines, strips, and so on. So this would be the second way that we could easily just import a CAD file, build the model, and begin begin working on that model so we can get some results out of it. The third modeling option in order to get a model just built or get a model into the program would be using Revit model. So I've already used our adapt Revit link to extract a model out of Revit, and if I import that data, I'll go to generic adapt file, and we'll go and navigate just to that IMP file that we've created. So here's the base model. It's just the generic adapt exchange file is called a .imp. I'll open up the import options. In the import level, I'm just going to import level 4. Actually, let's do level 3. 4 is a transfer level. And then we're going to create a new model. I can merge similar slabs into one unique slab if needed using this option. And I also have the ability to select loads and load combos if those are included in the Revit model for this case. So we'll say OK. The program imports that slab, and now I'm left at the same point I was with the previous couple of models. So those are 3 ways to get a model built inside of Builder. Now, there's also the ability for you to just simply model from scratch. I'll just show you quickly a couple of things that have changed in our modeling interface. So I'm going to turn on my grid settings here, and we'll just do a 10 by 10 grid. These are not grid lines, they're just the background grid that we can snap to. And new to the program beginning Monday, build 2, as I mentioned, is if I build a model, and I'll use my build toolbar now instead of my transform. Let's say I build a slab. You'll notice when I begin modeling, the program allows me to see these dimensions. Let me go back and try that again. So the program has some dynamic dimensioning similar to other modeling interfaces. We have a linear dimension and an angular dimension. We also, if you right-click and look at dynamic dimension settings, you can create different increments for length and angle. In this case, my length is set to 0.5 feet. I'll set it to 1. Or I can turn off the dynamic dimensioning. When I click, there's also extension lines. So this would be a horizontal extension, and then we have specific vertical extensions you can see along that extension line that shows up, that dashed line. We also have perpendicular extension, which is shown like so, perpendicular to the previous point or line that was generated. For any given slab that you model, you can right-click and you can lock out the length. You can input a length, you can input an angle, or you can lock the angle. So let's say I want to lock this length at 20 feet. I can lock the length. It locks it at 20 feet, and now I'm just able to swing the cursor around with that locking, and the angle changes. Or I can go ahead and lock out my angle. So let's say my angle is 45 degrees. I want to lock that relative to this point, and now I'm able to create a line at any length with that angle locked. So that's some new stuff. If I go ahead and create a model, some of you may have used our undo redo buttons, which unfortunately have not functioned great in the past, and we'll be forthright and upfront about that, but we've done a lot of work in just cleaning some of the just basic modeling functions up in the slab. Now if you press enter, you can close a polygon. In previous versions you had to right click and close. Enter works for any polygon. You can also, if I wanted to undo, I can just simply undo the slab, redo, undo, redo, and so on. I could also backspace. If I'm in the modeling of a polygon command and I model something and something goes wrong, I can just use backspace to go back to a point, and then I can just start over where I was in backspace. So there's some new improvements that are really nice in this version. We will have some information about it beginning next week, both in video form and also some literature that you can use to explore some of the new hotkeys and the new functions in Builder. We're going to go back to our previous model that will be kind of our working model for the remainder of the session, and we're going to use this model as the base model. So this model right now is shown in just shaded view. I'll turn that back over to wireframe, and we'll go here to wireframe. I'm also going to turn off the grids and the dimensions. They're in this case they're in the way, so I've grouped my grid lines and my dimensions. If I double click on any of these, you can see they belong to grids and dimensions group. And if I use the group library, I can go ahead and just turn off that particular group, and it turns off the display. So for this model, we're going to first set up some criteria, and then we'll go ahead and load the model, set up combinations, generate our design strips, and process the model so we can show how we're going to get results out of this two-way slab. So the model is in place. Just from a material standpoint, we're using under the material concrete. This is going to be an SI today. We're using 27 MPa. That's roughly 4,000 psi concrete, and that's set for both the columns and also the walls and the slabs. That's everything essentially. We also have the ability to set up mild steel material properties, as well as if you had any generic type of material in the model, maybe you had a steel column or a post or something, you could actually model that component on the slab in this case. So there's also the ability to model material generic as well. For criteria settings, we're going to go through these different settings to set up our criteria for this slab. We're going to use ACI 2011 for the design code. The option for crack width is available when you do a two-way RC slab in Builder, or it could be a one-way, just an RC model in general. So this option for reporting crack width is available. If I select yes to that, we also could take it a step further, and we could limit the crack width. So if I select the option to limit the crack width, we would input a limiting value, and the program will actually use the methodology outlined in the European code for, number one, calculating the crack width, and also for determining how much reinforcement is needed and at what spacing to limit the crack width to this value right here. And if you go to Help menu, that basically outlines how that's the reference by which that is being performed in the program. For this model, we're just going to select no. I will turn on the reporting of the crack width for the model. For two-way, one-way, and beam, if you have different types of criteria, let's say for design purposes, you have different strength reduction factors relative to this particular code. So notice that if you toggle between any of these three, you can set the phi factor differently, again based on the design type. For reinforcement bar lengths, the program allows us to input the cutoff lengths for minimum rebar, bar extensions for rebar required for ultimate or demand actions, and also we can also use some adjusting of length. So for example, if we wanted to center a bar, all of the bars over the supports, we can use the option to adjust length and center bars. That can be done also in the bottom of spans, let's say, for bottom reinforcement. And you can also choose to enter the position of the bars on the plan, which means that it's going to create a dimension from some anchor like a column or the end of a wall, showing you the dimension to the bar extension past that point. There's a question. Let me go ahead and answer that. Yeah, so the question was, run back over access to group library. Certainly, I'll be happy to do that. So let's say we wanted to group our columns for some reason. Right now, the columns, if I double click on a column, the group is just the default group, which is group 1. So the first thing I would need to do is I would need to create a group. And if I access the group library, here it's the blue eyeglasses with the little G icon. I'll create two new groups. One group might be columns, and the next group I'll just say is going to be walls. And nothing has been assigned to these groups yet. So excuse me, the phone rang there. But if we now go ahead and just select all of the columns, and there's different ways to select components. I could pick each one and press Control, which is probably too hard and too time-consuming in this case. Or I could use Select by Type, select Columns, and I want to make a modification to all of these columns at the same time. So I'll go to my Modify Item Properties, and I'll just reset the group and assign these to columns. And then I'll do the same for walls. I'll select all of my walls and assign those components to walls. And this is helpful, especially like for a PT slab, if you're modeling a lot of tendons and you want to differentiate between banded and distributed or different zones, you can group tendons. So now I can go to group display. I can turn off columns. I can turn off walls, and so on. Now that was an example. In reality, you probably wouldn't need to group columns and walls because we have under user interface, we have the ability to turn on structural components display toolbar. So this toolbar here allows me to just turn off the columns and walls to begin with, just as a default button that allows me to isolate different components in display. All right, so we'll continue with the criteria. For a rebar minimum cover for the two-way slab, we'll go ahead and we'll just say this is 25 millimeters top and bottom. Now it's important to note that we're defining right now the outer layer of reinforcement. So this is the cover from the extreme fiber of the concrete to the longitudinal bar. And this bar is outer layer. So we have to define at a support line level what is the outer and what is the inner direction. Either the X or the Y directions will become outer or inner. Program will by default select X as outer, Y as inner, but you have the ability to change that at a support line level, and I'll show you that when we model the design strips. Under preferred reinforcement size, we have a few default libraries for the selection of units. So the user can modify this at any time. You can just click to edit, and if you wanted to write different names, for example, for a bar, this bar could be named Spencer, it could be named whatever you want it to call it, or you can just restore the default. You can also, even though the model is working in SI units, you could technically use US bars for this model and mix the bar sizes with the actual program units that we're using. So you can select that system here. Preferred bar size, we're going to say here we're going to use number 16 or 16 millimeter top and bottom. And then stirrup size, if you have beams, you could define the preferred stirrup size. For any bar type, bottom bars, mesh, reinforcement in a slab, stirrups, punching studs, etc., you can define which mild material, mild steel you're going to use. And in this case, we only have one material defined that I showed earlier, so the program will just default to that material. For shear design options, for punching shear in this case, we have two options. We have stud rails and also stirrups. So for stud rails, we might, let's just use a 10 millimeter bar for stud rails, and the program allows us to input the number of rails per side. Currently, you must input the same number of rails per side. That will change coming up this year for new and improved punching shear module in ADAPT. And then we can also determine if we're going to check punching in each direction for moment in isolation, or if we want to use a combined effects of the bending for the punching shear check. Rebar roundup. This is probably the most widely the most widely misunderstood option in the program is this bar spacing option. We want to make sure we cover that. So there's another question. When does new and improved punching shear module come out? We plan on releasing it in version 2018, which is planned for this year. So it's technically the fall of this year is the tentative release date. The 2017 version of the program will be out in May, June of this year. That will include wall design. It will include tendon modeling improvements, being able to swerve tendons, being able to modify CG of tendon groups on plan, showing the CG and just modifying instead of having to open the tendon dialog and generating the modifications there. For version 2018, the main features for that version will be P-delta analysis, punching shear, and also beam, let's say more straightforward discretized beam design inside of Builder for integrated beams that might be part of slabs. So those are the three main focus points for Builder 2018. Okay, so we have the ability to generate some rebar roundup spacing. This is just the bar length roundup value. So if your bar is some particular length, the program will round it up by this amount, and then this bar spacing round down is shown here. This is just a conservative approach to kind of normalizing the spacing between bars and the lengths of bars. The next option, bar spacing, again, this is very important to understand the output in Builder. When you have this option deselected, and it's always deselected by default, the program is going to add reinforcement to your slab which meets these spacing requirements. So in this case, it's either 500 millimeters or 1.5 times the slab dimension. In this case, our slab dimension is 275 millimeters thick. So the program would enforce a spacing of bars of 410, 412 millimeters because this is deselected. And I'll show you how that presents itself when you output the reinforcing. The last thing we want to do quickly is look at the analysis and design options. And again, this is similar to if you're doing a PT design. The only difference really is this option for column and middle strip. There are a few other things related specifically to PT that are not shown here, but the most important thing again for a two-way RC slab would be this option, column middle strip, in terms of how the modeling is set up and what the program is producing from a result standpoint. Also, for the supports at the far ends of the walls and the columns, right now the default is set to a roller support and rotationally fixed condition, which makes sense for a post-tension slab where we want to make sure that we're accounting for shortening of the slab. But for an RC slab, it may not be as important. So we're going to change this single level condition to, let's just say, pinned at the bottom. So we'll go ahead and turn off the rotational fixity, and I'll just user define my supports at the base. And we'll say OK. That sets up our criteria for the model. We'll go ahead now and add some loads. So I'll add some surface loads to the slab, and we're only going to consider gravity loading today, but we'll go to loading, add load, or we could also use the loading toolbar. So I'll pull this toolbar out, and we'll just use this option. If I select the slab, I can map loading to the slab using the patch load wizard. We'll say the dead load in this case is 1.5 kilonewtons per square meter, and then the live load, we're going to say that the live load is, and I'll use the pull down menu, the live load here we'll say is 3 kilonewtons per meter. So we have other load types from a gravity perspective, point load, line loads. Regular patch load means the user would input the load. So if I used a regular patch load on top of my current load that is mapped around the entire slab, I'll just go in and create this patch load. And that patch load we're going to say is a live load of an additional 0.5 kilonewtons per square meter. So because I have essentially two loads in the same spot, I have 0.5, but I also have 3 kilonewtons per square meter for this entire perimeter load, or it's really a uniform load. These two are superimposed. So in this region I have 3.5 kilonewtons per square meter. If you needed to deduct load from a region, you technically could use a negative load input in the program. So if I do negative, this is just in the opposite direction. Okay, so we have some loading in our model. From the loading load case library, the two default reserved load cases are superimposed dead load and live load. This should not be confused with self-weight. The program will add that automatically to all of the load combinations that it creates for you, and then you have the ability to add and define factors to self-weight for additional combinations that you create, and we'll show those combinations here in a moment. So we have dead and live. We could also add additional loads using the add function here. I could add a load and rename it. Maybe this is snow load and so on. The reducible button here, it doesn't really apply to this loading. This is used for column reduction, live load reduction for multi-story applications, so this should not be used in this sense. It's not going to really do anything if you did select it, but it doesn't really apply to what we're looking at today. You also can add temperature and shrinkage in a slab. So if I added temperature, for example, I'll go ahead and add another load case, and I'll call this temperature temp1. I'll mark it as temperature, and you can see that it actually creates a T designation which signals that it's a temperature load. Snow load is not temperature, so I'll get rid of that. There's one question here. Yeah, is there an easy way to do skip live load? And how about moving loads? Moving loads, I would say no, there's not currently an easy way to do that other than to use the skip patterns and move patterns around in certain locations. So you could create, for example, 10 unique skip regions and then define loading to those regions and then turn those regions off and on in load combinations. So that's really a customized, very customized way to approach moving loads, Aaron, that I can show you. I think we have a video about that on our YouTube channel. But for skip live loading, it's fairly straightforward, and I'll show you how that looks here. If we go back to a plan view, and I'll just go back to my default display. Let me turn off the view of the supports. So right now we have loading basically on the entire slab plus some additional patch load here. And when I run the model, if I look at my load combinations that the program is stored, I have basically 5 combinations shown. And those combinations are going to be evaluated per the analysis tag that we have associated with them. So we have service total, service sustained, strength, initial. And initial in this case doesn't really matter. I'll just get rid of that. We're also going to note that for each of these combinations we have just some factor applied to the entirety of the live load in this case. However, we may want to run through multiple patterns where live load is off and on for a particular pattern. So if if we look at this, we'll go to loading, skip patterns. First thing I have to do is create subregions for my patterns that I want to apply to the structure. So when I apply a subregion, it's almost like I'm going to be drawing grid lines through the system. So I'll just take this line, I'll use my orthogonal tool, and I'll just close these lines. I'll just draw them. Let me do that again here. It created two there. Let's go back to loading, skip patterns, create subregions. Let me turn that off for a moment. So there's line 1. I'll say close. This is going to be line 2. Close that. Line 3, and we're basically just creating dividing lines between locations in the slab that will create unique regions that I can then use to apply patterns to. So you can see I've created 1, 2, 3, 4, 5 lines that will subdivide the slab into regions. If I go back to loading, skip patterns, define and edit load patterns. Each one of those regions now creates a small little circular handle which allows us to grab the region more easily. So I can now define my patterns based on the availability of the regions that are selected. So I'll choose to reduce my live load. I can also include a skip factor if needed. The first pattern I'll just say will be reduced live load, but all regions selected. So we'll add that as pattern 1. Pattern 2 might be something like this. Pattern 3 would be something like so. And then pattern 4, do that. Pattern 5, and then we might do like a checkerboard type situation for the last pattern, let's say. We could have as many patterns as you need. So we have patterns 1, 2, 3, 4, 5, and 6. And the loading is applied in these areas where we have the hatching. Because I've reduced the live load, you'll notice that there's a reduction factor shown which is based on the area of this region. So when we apply the live load for those patterns that we've defined, going back to skip patterns really quick, each one of these patterns that's applied for that given pattern, or each set of live load I should say that's applied for that pattern will be reduced by some factor per this checkbox that we've selected. Okay, so each pattern then becomes available in the loading menu. So if I go to my load combinations menu, I now have some new additions to this menu. I have the skip live load max, skip live load min, which is essentially an envelope of all of the patterns, and I also have individual patterns that I can define factors for and include those in combinations. And then the evaluation of the combinations is essentially the same. If you choose to use patterns in lieu of live load, these patterns, like I said earlier, have reduction factors applied to them. So that's the way you can enter skip patterns in your model. And I'm going to just use my default combinations today. So the next thing we want to look at is the crack deflection. And I'll set this up rather quickly. We're quickly running out of time today, but I may go a little bit over for those that want to hang around for an extra 10 to 15 minutes. If I go to loading combinations and I look at this, each one of these combinations that will be evaluated is going to be done based on an uncracked condition for all of our components. But we want to know whether or not the slab is going to crack. And if we just completely bypass the crack deflection check, you always have the ability to just input some stiffness modifier. So I could go into the slab here, go to modifier, edit usage. I could say I want this to be a cracked condition, and then I can modify the flexural and axial stiffness of a component and just force it to soften and give me more deflection. That obviously may not be as accurate as actually having the program check for crack deflection. So we're going to do this more precisely, and we'll go back to loading combination, and we will set up a few combinations here that are going to tell the program check these combinations for cracking. And for those of you that might be familiar with ADAPT, PT, and RC, I'm going to set this set of equations up or combinations up similar to PTRC. So we're going to have 3 unique crack deflection combinations, and I'll first set this to crack deflection, and I'm going to add 3 combos here. The first combo we're going to call self-weight only. The second combination we'll call self-weight plus SDL, and this is just sequential loading patterns that I'm adding. The third we'll say SDL plus live load. If you had a post-tension slab and you were doing something similar, the second combo would really be SW plus PT, and then the third would be PT plus SDL, and so on. So there would be 1 additional load case included, which means you'd have 4 of these combinations potentially, or maybe even more depending on what load cases you're evaluating. So this is just going to be 1 times self-weight. So I'll just add the 1 here. The next one will be 1 times self-weight plus dead load, and then this will be 1, 1, and 1 times live load. So for each of these 3 combinations, the program is going to check and determine whether or not the slab has cracked under the loading or under the action and displacements relative to the load applied for each of these combinations. In addition to this, I want to go ahead and extract out my superimposed dead load and my live load, considering the crack state prior to those loads coming onto the slab. So in order to do that, I can't just set up a combination for SDL and live load individually. I'm building these combinations sequentially so I can extract out those 2 conditions. So I'll now use this option for long-term deflection, and this naming gives kind of a false, it gives a little bit of a false idea that this is only for long-term deflection. In reality, this means that you just simply can take results from one combination and add or subtract it from another combination, or apply a multiplier onto it. So for this new combination, this is actually going to be called SDL only. And I'll do 1 more, and this will be live load only. And there will be a last one, which is going to just be called total deflection. I'll just say total long-term deflection. And so for SDL only, I'll go navigate this all the way over, and I'll filter this out by combinations now, because that's really what we're referencing. So for this combo, we're going to say this is self-weight plus SDL minus self-weight only. For the next combo, we have self-weight plus SDL plus live load minus self-weight plus SDL. And that allows us to extract the live load and the superimposed dead load combos and combine them here. The total deflection combination, we're going to just assume a creep factor of 2, and we're going to say, okay, we have essentially 3 times, we're going to take the instantaneous deflection times the self-weight only plus the creep associated with it, so that gives us 3 times the self-weight only plus 3 times superimposed dead load only. We'll say that superimposed dead load is sustained, and then we might say, well, live load is not all sustained, so I'll just apply a creep factor of 1.5. I'll just say this is 2.5, just for some arbitrary modification to the combo. So we now build a combination by embedding the creep factor into the multiplier for this long-term total deflection combo. when you reference other combinations, when you reference another long-term combination inside of a long-term combination, they have to be built sequentially. So this last combo references this one and this one, and these all have to come sequentially. If for example this was moved up to the top of the list, then you would get garbage results because it's referencing combinations behind it in sequence of how things are being solved on the back end of the program. So that will be our set of crack, deflection, and combinations, and just for our deflection evaluation. The last thing we want to do before we analyze a slab is we want to build the design strips. So I apologize if I'm moving fairly quick here. I want to try to get through what we have today. We'll go ahead and just select. Let me make sure I have all of my components turned on. I think I have openings in this model that need to be turned on, so let's do that. Yeah, there's a few openings here. So we're going to generate the strips in the X and then the Y direction. In the very first model we looked at today, everything was set up for us because we used the floor wizard. But in this model we have to define our column strips, and then the program will generate the middle strips. So I'll define the column strips just by manual input using create support line. We're going to say that these are X direction strips, and if we go to the design tab, remember how earlier I referenced the outer and inner layer. So we're going to say that the rebar in the X direction is going to be referenced as the outer layer. The rebar for the Y direction will be underneath it, top and bottom, or let's say inside, and set as the inner layer. So, and then the criteria for design will be a two-way slab, and we'll go through and just set up our strips here. So we're going to start at the slab edge, and I'll go ahead and navigate to each of the supports, and then we're going to close this off at the perimeter. I'll say C to close. When I hit a wall, just go perpendicular or snap to the end point of the wall. And we have this big opening in the middle, so this could be left to the user's interpretation. In this case, I'm going to just stop my support lines off at the wall, or I'm sorry, at the face of the opening. So we'll go perpendicular, I'll go to face, and I'll stop the support line, and then I'll pick up this on the opposite end, and I'll just start a new support line at the opposite end. So we'll go ahead, and I want to show how the program creates middle strips in this case. And we'll also need to add some splitters for this condition because I have two support lines terminating within the perimeter of the slab. So let's go ahead now and create this last few support lines in this direction. You'll notice I'm kind of going back and forth between the snap tools because I have snap nearest turned on, which tends to snap to points that I don't want it to snap to. So let's do this. And then finally we have that. Okay, so that's the X direction. For the splitters in this direction, because again these points terminate inside of the slab, I basically need to create a boundary. That boundary is going to look something like this and like this. So I have to have some virtual boundary so the program knows, okay, I'm going to take this tributary for this strip and I want to terminate it at this virtual boundary, and this becomes my column strip, and then the same thing on this side. This becomes the column strip here. But in order to do that, I have to define these things called splitters, and some of you are probably really familiar with splitters. So we'll go ahead and create a splitter. The splitter will be in the same direction as the support line. So it's labeled, I shouldn't say in the same direction, it's labeled the same direction as the support line that it influences. So in this case it's the X direction, and I will navigate up and I'll close that off at the support line above and below on each side, and these are these virtual boundaries that I was referencing earlier. So now if we go ahead and just generate our strips, I haven't done the Y direction yet. I'll add those here in a moment. You can see that the middle strips, and I'll turn on that special reporting mode, report plans, to show these strips. So we have a column strip and a middle strip which happens to go right through this opening. We could bound this off again with splitters to try to customize that area, but we'll leave it alone for now. Notice that this column strip here stops at the opening face. Therefore, the middle strips above and below are mapped to the same length of that support line, so they also stop at that location. And you can see this strip here, this column strip, actually floats down, and it's actually it cuts down into the region where these two support line 19 and 17 terminate. So it's important for the user to review what's happening with middle strips when you have splitters and cut off support lines, and make sure that they look correct. If they don't, and you feel that they should look something different, or you want to force the program to do something different with the strips, then that's where turning off the option for automatic middle strip may come into play, and the user can then go and define specifically where you want the middle strips to occur. So let's go ahead and generate our support lines in the Y direction. I'll change the direction here to Y direction. Notice also that the design now needs to be changed to inner layer, and I'll start at the left side, working my way from bottom to top, just using some standard. It's probably a good idea for users to do that. There's also a wizard which allows rapid input of support lines. I like to do this manually just to show those who might be new to the software how these should be done without having the computer just do it for you and relying solely on that method. So we're just snapping again to the support points. This just simply defines the spans along each of the strips. And in this case, we're not going to add any splitters. We'll just leave it as is. So our entire set of strips looks like this. We have both X direction and Y direction strips, and I'll use my support line toolbar. This allows me to turn off and on the design strips, so I can turn those off in the X, turn them on in the Y, and vice versa. Now we're ready to evaluate the slab. By the way, this is cutting all the way over because this strip right here terminates at the slab. It's actually short because of this corner that turns up vertically. This one extends up, this one does not. If I was to move this out of the slab, like so, and regenerate my strips, I would now get that broken out how you might want that. So this now looks something like this. This now extends over. This doesn't cut all the way over to that edge because I've now extended the other column strip vertically to be aligned approximately with this one here. So one thing to remember, the middle strips are really just going along for the ride. What's being modified by the user to be able to manipulate and create the strips is the column strips that you add to the slab. So we'll go now, and the last thing we're going to show here in the next 10 minutes before we exit for today will be the process of evaluating the slab, checking the deflections, and then generating the rebar. So we'll first mesh the slab, and I'll use a 1 meter mesh, and I'll do node shifting at 1/2 of a meter. We'll mesh the slab, and then I'm going to analyze the structure. So I'm analyzing this as a single level model. I'm going to analyze it for all of my load combinations, including the patterns. Even though the patterns are not included in the combinations because I have set them up, I'm still going to get some solution for them, and I can always look and review those solutions, but they're not included in any of the design or deflection combos. We also can define which stiffness case or modification case I want to use. If you recall, I set up this cracked condition for the slab. I'm just going to evaluate this as an uncracked slab, but I am going to check the crack deflection. So that will be an extra step in the process. And we'll go ahead and analyze the slab. This window here, just ignore that. That's just an internal window we use to see the input and how it's being processed. So that's the commercial version does not have that included in it. After we run the analysis, we're going to design the design strips. In order for the crack deflection check to be evaluated and to work, we have to run the design of the reinforcement in each of the sections, because we use that to determine some of the data necessary to do the cracked analysis. So the slab has been evaluated. If I stop at this point and I go and I look at the deflections, for example, the Z deflection, these deflections that you see now are for the uncracked condition. You can see this is, even though I have cracked deflection combinations set up, I have not checked cracking. So everything right now is related to uncracked slab conditions. We'll go ahead and take this a step further, and I'm going to design the design sections. So now I'm evaluating the section cuts and the strips for reinforcement in the slab. And one thing that's important that we're going to show again is that option for spacing reinforcement in the slab. When the program evaluates the sections, it's going to evaluate every design cut for both minimum rebar, which should not be confused in this case with spacing reinforcement. Minimum rebar is really temperature shrinkage steel for a two-way RC slab in the sense of Adapt Builder or Adapt Floor Pro. It also will calculate every section for whether or not it needs reinforcement to meet the ultimate demand moments or axial tension in the section. And if any section requires either of those two items of rebar, service or strength, what happens is the program will then apply the spacing to that section. So if the output of rebar for service or strength, let's say, results in a maximum of 1,500 millimeter spacing over the width of a strip, the program says no, the spacing limit is 400, and it will actually add additional rebar to meet that spacing limit in the slab. And I'll give you an example of that now. So we haven't done the crack deflection yet. That will be the last thing we look at. But if we go and now and I generate my reinforcement for my envelope. So I'll just generate for envelope. We now get a bunch of rebar on the screen, and the rebar is a function of the design strip width. Every piece of rebar or every set of reinforcement is always assigned to the width of the strip that it belongs to. And using the reinforcement toolbar, I can isolate some of this so it's not as messy on screen. And I'll just turn on, let's say, the X direction bottom reinforcement. And this is the program calculated reinforcement in the bottom of the slab. And you can see along this strip, I'll use this span right here. If I turn on my strip, in this span it says I need 13 16 millimeter bars. If I open this up and I look at builder sum, and again, for those of you familiar with PTRC, for this strip, this is number 2. It says 13 16 millimeter bars by so many meters in length. So here, this 13 16 is matching what we have graphically shown here, and it's spaced at 275 millimeters. What that means is that the criteria for the spacing check, if I go back to, where is it? Here we go. bar lengths. Under the spacing, the max or the minimum spacing requirement was about 410 millimeters. So because the outcome of the strength and service check was 275, this never kicked in and controlled. Now if I change this and I say no, I need the spacing to be at 100 millimeters, and I go back and I just regenerate my reinforcing, I currently have 13 bars. I'll just go ahead and reset the display. Now I have 35 bars because now it's applying the spacing check on top of the round down, and I have triple the number of bars I needed just to meet service and strength. And you'll notice again, if I go into Builder Sum only reports the rebar necessary to meet service and strength. So again, I'm still only showing 13 here, but on screen the program applies the spacing check to the output of rebar when you run the graphical display of reinforcement. So that's important because we get a lot of questions about that in support. Why does my rebar look different here versus here? And this is typically the reason for an RC slab. So if I just say, well, I know I'm either going to have a rebar mesh in the slab, or I'm going to meet that minimum spacing requirement somehow, I'll just turn off the bar spacing, and if I regenerate the drawing for reinforcing, and I'll just reset the view back to bottom in the X, I'm back now to my 13, 16 millimeter bars. So there's a question here. Yeah, why was the spacing 75 millimeters when you set it to 100? Pavel, there's some round down. If you recall in the criteria, there was some spacing round down that was happening. So the program is applying some of those round downs to the actual strip width that we had defined for this one strip. And I just didn't pay close enough attention to all the round downs and what I had set up in the criteria. The user also has the ability to add reinforcement to a slab. So in this case, I have the program doing all the work for me. I'm allowing the program to calculate all of the bars at the top and bottom in the X and Y directions. For example, this is the top bar represented by the green, and if I look at that in both directions, we have, easily definable reinforcement layouts near columns and in the middle strips at positive bending regions in the top. As the user, you have the ability to add rebar to a slab. So if you know you're going to add number 5s at 18 inches on center, top and bottom, you can go in here and map mesh reinforcing to a slab. I can use the wizard and I can say, well, I know I'm going to add that rebar to this slab, and we might use number 5s, or let's say this is, I keep forgetting this is metric, 14 millimeters at 300, both directions. We'll say okay, and that's bottom reinforcement I think that I just added. Let me turn on the mesh symbol and see what we have there. Yeah, so this is, I just added bottom rebar, and now if I was to recalculate the design sections and update the design, you would get less bottom rebar because now we have it, some of it displaced by this, what we call user-defined reinforcement. I'll delete that. So the last thing we want to do is, now that we know the reinforcement in the slab, we're going to go ahead and do the last step, and we'll just check the crack deflection in this case. The crack deflection, again, is dependent on the rebar in the section, whether it be user-defined or calculated, program calculated. So that has to be done prior to the crack deflection check in the program. I'm sorry for running late. We'll exit here in just a moment, but if there are any questions, I'll take about 5 minutes for questions after we're done if anyone has additional questions. So now that the crack deflection check is finished, we now can look at the results. So going up to the very top of this, let's just collapse some of this. We're going to look at slab deflections. remember that we set up 3 crack deflections. There was self-weight only. If I turn on self-weight only deflection, the self-weight only deflection is 8.65 millimeters max in these green spots, let's say. And this is an uncracked deflection. We're just assuming linear elastic behavior in this case with no cracking occurring in the slab. However, since we calculated the crack deflection, the program also gives us a cracked result as well. So the uncracked is 8.65 millimeters. The cracked deflection, if there was any cracking that existed for a self-weight only, is 9.51. And for any cracked combination, I can look at reduced stiffness about the X and also about the Y axis. So this shows me where I'm losing stiffness. This is basically I effective over I gross on the scale. In addition to that, we can look at, let's just skip down to cracked self-weight plus superimposed dead plus live load. So if I look at that deflection, this is essentially all load, and let's see, this is, did I update that? Let me make sure I apply that. Okay, the scale didn't change there. So this is 25.2 millimeters of deflection, and this is with all of the load applied considering cracking. If I look at the uncracked condition for the same set of loads and I apply that, the deflection is 14.6 millimeters. And looking at, let's go back to the crack just to look at the extent of the cracking once you apply all of the load. And this doesn't even consider long-term effects. So if I now look at the reduced rotational for the X and the Y, you can see it's cracking in many more locations than what we had just for self-weight only. So this shows you those cracking locations in either direction. The final deflection in this model, for just to curiosity's sake, crack total deflection per the deflection combinations that we set up. We'll report that here. Oops, I need to go to Z direction translation. So it was 69 millimeters. So too much deflection. It's like 2.5 to 3 inches of deflection there. So I assume that won't work for this design, but again, this is just exploratory in nature. So that will conclude today's webinar. If there are any questions, I'll stay online here for the next 5 minutes or so. Again, I apologize for going over, and I appreciate everyone's time today. Thank you. Yeah, the question is, where will this be recorded? Where will it be posted for review? I will send this to all persons that had registered for the webinar, and we're also going to likely post it online on our YouTube channel. There will be a new playlist with webinars there, so you can check our YouTube channel once the recording is available here. I would say try Monday. That's when the email will be sent out to attendees. All right, looks like no one else has any questions. Here's a question, multi-level question. Does the design criteria apply to all levels, or are you able to set different criteria per floor? Brian, it's a good question. It would apply to all levels. It actually applies to all design strips. So if a design strip, let's say, on any floor is set to two-way slab. The criteria really applies on a per design strip basis for the reinforcement centric settings. For analysis and design options, this also, the only one that really applies to single level versus multiple level would be the support conditions. Okay, looks like there's another question here. Is there a workaround to set different cover for different levels? The answer to that currently is no. You would have to change. Right now, the way the program operates for multi-story is after you run the analysis multi-story, you actually have to go to each individual level and design level by level if you're going to process the design section. So if you want to have different covers per level, you would actually have to go to the criteria prior to analyzing the current, or not analyzing, but designing the current set of design strips for one individual level and modify it manually. But we can add it again as a feature request to be able to produce different covers per levels. Can we now copy the live load strips on different levels, the patterns? Pavel, the patterning, as you know, is really it's a byproduct of single level analysis. And when we built out the program for multi-level, it was never applied to a multi-level model. That's not to say it can't be done, but what needs to happen for doing live load skipping on a multi-level model is you really should, my recommendation is for you to set up skip regions on every level, so you're going to have unique skip regions on each level, and then you're going to have to create patterns on each level. Yeah, can you copy up the skip regions? You can. I would copy up the skip regions, but I would create new patterns because the patterns that were previously created belong to the floor below, let's say. So you can copy up the skip regions, but you have to define new patterns once you copy them up. Okay, other questions? I'll go into auctioneer mode, going once, going twice. So if there are no more questions, we'll go ahead and conclude. Again, I appreciate, we have one more question here, just in the nick of time. Aaron, the skip patterns do only apply to the specific floor. So they would apply only to the floor that they are assigned to within single level mode. They do not apply to columns. We covered column live load reduction last week for the webinar last week. So if you'd like, Aaron, I can answer that offline, how do you apply live load reduction to columns. I believe we have a video also that covers that topic. But what we talked about today only applies to floors. So. All right, well, thank you, everyone. Again, if you have any questions, please feel free to call us or email us at support@adaptsoft.com. Thank you.